and kinetic energy. Just as a review, well, this whole thing on a review, but this is all the stuff we've talked about so far, okay? All of it. This is like a really good cheat sheet, okay? If you can understand what this means, you're in decent shape. Yeah. I'm not going to spend a lot of time on this because we're behind, but it's in the slides. You don't have to all right, or you can just photograph it. So we talked about kinematics. That has to do with how stuff moves. Then we talked about dynamics. That has to do with why stuff moves. So if you have a force, that's dynamics. It generates acceleration, that's kinematics. And then you can project where things are going to go once you figure out the acceleration from the forces. Okay? Forces is just drawing a problem, identifying the forces, picking your axes, so you have some sort of perpendicular axis system, summing up your forces along those axes. That's always equal to mass times acceleration. That's Newton's second law. We use it over and over and over. Okay? We have a few special rules we just talked about with circular motion that introduces some new variables, a couple new concepts like frequency and period and all that jazz. So all of this stuff is included here. Okay? And over here, remember, even though we have all these kinematics equations, they all come from calculus, and these equations are assuming that acceleration is constant. If acceleration is not constant, you have to go back to this. So this is true always. These are true in specific cases, but ones that come up a lot, so we write them as their own thing. Okay? It's always good to remember, where did your equation come from? Some equations are definitions, right? Period is a definition. It's just the amount of time it goes around once, all right? But velocity has a mathematical definition. It looks like this, okay? And then if you want to go back and forth to get these equations are not a definition. They're a consequence of treating acceleration as being constant and then using this. So remember, you don't have to know how to do the derivations, but you should know when we get an equation like this, what the premise was, where did it come from, okay? Because otherwise, you won't know how to use it. So, cool. Let's talk about work. Then we'll talk about sort of how kinetic energy and work go together. We'll talk about when force, so up until now, most of our forces have been constant, right? Weight is pretty much constant if you're on Earth. So that's the force due to gravity. If you have normal forces, they generally aren't changing over time. You pick one, you stick with it, okay? So we're going to now have to deal with what happens when forces change over time, because that's the true nature of life, right? Most forces change over time. When you kick a soccer ball, you don't just kick it and at one instant you get one force and you're good to go. There's an amount of time that your foot's in contact with the ball, and the force of the ball on your foot and your foot on the ball increase and decrease over time. Okay, so we're going to have to deal with how that works. All right, and that's actually more into impulse and momentum, but that's right around the corner. In fact, it's in the lab, so sorry. And then we'll talk about work and energy with varying forces. When we say varying, what kind of math do you expect to see? Calculus. Okay, so we're going to be, I did say energy's easier. It is. You can just never get away from calculus, I'm sorry. And then we'll talk about power, which is just work over time. All right. So let's talk a little bit about some definitions we need to understand what's going on. So what is a system? Okay. This is a very abstract concept, but it's pretty important. So the system is a small subset of the universe, okay? And you define just like with your coordinate system, you get to choose your system, and where you put the boundaries of your system are going to dictate which things you call which variable, okay? So you set the initial conditions, and then you can figure out the problem from there. As long as you're consistent, you should still get the right answer no matter which system you pick, all right? So examples of valid systems: single object or particle, collections of objects or particles, okay? a region in space that can change size. Okay? So for instance, if you're doing a problem with this, I always use this for post-it note, it's getting really beat up. But when you're using this post-it note pad, okay, this can be your system. So the boundary of the system, if we're choosing the post-it note pad, is the outside of the post-it note pad. So am I part of the system?
No. Yeah. No.
No, I'm outside the boundary, right? I'm interacting with the system, but I'm not part of the system. Okay? So when we figure out things like forces and energy, we're just talking about the post-it note. We're not talking about my forces and energy. Any force or energy that I impart to this system would be considered external. So if you want to calculate the work that I do, that would be the work external. Okay? If you want to calculate forces I apply, those are external forces. So for instance, how many of you are familiar with the concept of kinetic and potential energy? So most of you? Okay. So crash course. Potential energy is energy stored by position. And we'll get to like the details of all the math of that in a little bit. But for instance, this post-it note pad has potential energy. Where does it get that potential energy?
Gravity.
Gravity. Okay? So it has so we're getting to this point, but what I do, let's say this is on the floor. Okay? If it's on the floor, it has less potential energy than if I lift it up here. Alright? The way that I give an object potential energy is I do work on it. Now, it's not a lot of work because it's a light pad. Okay? A light post-it note pad. But when I lift it up, as I lift it higher and higher, that's more and more work done on the post-it note. I'm doing the work, which gives the post-it note potential energy. Okay? Now it has potential energy. Once something has energy, you can change the format of that energy. Okay? I can turn this into kinetic energy. What do I have to do then? Okay? So I did work. I added energy to the system, and when I say the system, it sounds fancy, but I just maybe had post-it notes. Okay? So here I am. Oops, I dropped it. Adding energy to the system. Now it has stored energy because of its height. Okay? If I drop it, I change all of that potential energy into kinetic energy. Okay? Is that feels good about that? Okay. Cool. So a system can be anything. So for instance, if you wanted to treat the system as me and the post-it note, okay, now any work that I do on the post-it note, that's internal to the system. So you don't put it, when we do the equations, you don't call it work external, it just stays all inside the system. So it's just like when we're talking about forces. If we have 2 blocks and then the floor, our system that we chose was the 2 blocks. Because then any interaction with the floor, we don't include the forces that happen to the floor because it's outside of our system. Okay? So it just sets the boundaries of which objects you care about and how you define the variables. Alright, so this is a system boundary, it's an imaginary surface, which means like if you sort of like wrapped this in saran wrap, but it was invisible, that would be the imaginary surface. So everything outside the plastic wrap would be outside the system, anything inside would be inside the system. It's just an imaginary boundary that you draw in your mind. No, that's not funny. Okay, cool. So here's a question. So here's 2 options. You're going to help this guy move. He apparently owns a lot of heavy objects. He has an amp collection to go with his cats. But he's only moving next door. Okay? Or you can help this guy move to San Diego. Okay? So imagine you're an incredibly lazy friend. Which friend are you going to help move?
Pillows, so they can sleep on them.
From pillows.
This is just all terrible. Why?
Because there's a lot of mass you have to move, and that's
This is
a lot of distance.
mass over a short distance, mainly a lot of weight. Because what are you going to have to do to move the boxes, right? Well, hopefully you lift with your back, right? So you lift the box, right? So
Lift with your back.
Lift with your obviously.
No, I got it, but I was just like, you said it so like dry.
Yeah, sorry. So you have to pick up a box, right? Gravity is pulling the box down, so you have to do work against gravity to lift the box, okay? But you also have to consider the displacement that you have to, so how far you have to move things. So you're also going to be doing there's some force that comes from like the chemical energy that you burn. So forces that go on in your body, forces that work as you move to the side, okay? So you're going to be doing work over a short distance. So you apply force over a short distance, okay? This is a small amount of force, but over a long distance, all right? So what work is made up of is both force and displacement. And they're both important, as you'll notice from these two situations. Even though you don't have to apply a lot of force here, it matters that the distance is long. Here, the distance is short, but there's a lot of force. So work is made up of both force and distance, okay? And they actually have a formal relationship, but we'll start with just sort of the general relationship. So work is made up of force times displacement, okay? And work is positive if force and displacement are in the same direction, and it's negative if they're in the opposite direction, okay? So the time isn't really coming into play yet. We're just dealing with force and distance. But we'll deal with time when we get to momentum and impulse, okay? So for instance, here's a situation where this guy pushing a rock up a hill, okay? If the rock is also moving in this direction, meaning he gets it from here to here, is the work he's doing positive, negative, or zero? Positive, okay? The force and the displacement are in the same direction, so he's doing positive work, okay? What if he pushes on the rock and it doesn't move? But he's applying a force, but he hasn't overcome static friction yet. That would be zero work because it's force, whatever the force is, times zero, okay? So that's work zero. It's not too bad. Here, he's applying a force upward on the rock, and the rock is moving this way. So probably he's being crushed to death. What kind of work is this? Negative work. So, but it's in terms of this guy. So this guy applying the force, he's doing negative work on the rock, which means the rock is actually doing the work on him. Okay, so the rock is doing the rock's force on him pushes this way. It's an action-reaction force, so equal and opposite. And if the displacement's this way, then the rock is now doing work on him. So it doesn't matter what your perspective is. Okay, so from the perspective of this guy, positive work, no work, negative work. All right. Yes? Oh, because the real definition of work is a dot product with an integral. And I thought you guys might want to ease into that a little bit. Okay. Well, let's do an example.
Example number 1. You lift a crate of mass 5 kilograms from the ground to a height of 1.3 meters at a constant speed. How much work did you do? So let's start by drawing a free body diagram of this. If I'm lifting something at a constant speed, that means the force that I'm lifting it up with here, F lift, is going to be equal and opposite to the weight, right? So there's the force, or the force of the gravity, which is mg. So those two forces are going to be equal to each other. And let's write down our knowns real quick. So the mass is 5 kilograms. And the height that we're going to raise the block, or the crate, is 1.3 kilograms, or kilograms meters. Those are our knowns. What's the main equation we're going to need for this? It's the work, right? So we can calculate the work for each of the two forces. It's equal to force times the displacement. In this case, displacement up and down. So we can calculate both. First, let's calculate the force, right? So as we saw, the force due to the lift, we decided is going to be equal to mg. And that's because if it's moving at a constant speed, you're pulling it up just enough to cancel out gravity. So those two forces are the same, and we can calculate each of them. So the mg, mass, is 5 kilograms, and g is 9.8 meters per second squared. So that's just 5 times 9.8, which works out to about 49, and a kilogram meter per second squared is a newton. So that's the force of lift. So from that, we can now calculate the work. So let's calculate the work done. So let's now calculate the work done for the lift. So here's the work. The work for the lift is going to be equal to the force of this lift times the distance traveled. And since we are lifting it upwards and it's moving upwards, this is going to be positive. So we have 49 newtons as our force of the lift, and our displacement is 1.3 meters. Right? So that gives us a newton meters joules. That gives us 63.7 joules. And finally, the only other one we need to calculate then is the work done by gravity. And that's just going to be the force of gravity, which is mg, times delta y. And this time we're going to make it negative because we're moving it upwards, right? Moving it upwards, this is our delta y here. We're moving it upwards and the force is downwards, so that means it's going to be negative. So it's negative 49 newtons times 1.3 meters. We end up with minus 63.7 joules. Okay, and we move it up at a constant speed, which tells us that the change in the velocity is 0. There's no change here, it says here, at a constant speed. So since the speed doesn't change, that means that the net work on the whole object should be 0. And that's consistent with what we have here, right? Plus 63.7 joules, minus 63.7 joules. So the net work is going to be 0, which is consistent with what we want. And that is example 1.
How would you calculate the work you do by just like holding the box here and not moving it at all? Like you still like get tired and stuff, and you still like lose energy.
So that's not specifically work, okay? Work has to come from force times displacement. Now you could maybe get microscopic work from the displacement of your muscles as they since they're going to be contracted, right? There's some movement there, but really what you're doing is you're expending, you're keeping your muscles hot. So what kind of energy are you using? Chemical energy, okay? So you're not doing work, you're expending chemical energy. So when you're burning calories, what you're doing is you're changing chemical energy into what?
Potential or kinetic energy.
Well, in this case, if you're not moving, if you're just flexing, right? Your chemical energy is probably turning into heat, and it's also changing around some there's some motion, some work being done on a molecular level, right? So you are going to still conserve energy, right? And that's how you're going to burn off some of the stuff you ate earlier. But yeah, it's a different situation. So it's not technically work, at least not in the macroscopic sense. Okay? All right. Oh, here's a riddle, and then we'll talk about. So why is kinetic friction so sad?
Because we cannot get the
It's because it only does negative work, or sometimes because it's a drag. But why does kinetic friction only do negative work?
It goes against motion.
Yeah, if I'm pushing something like this trash can this way, the displacement's this way. Friction always, by definition, kinetic friction always points opposite the direction of motion. So friction can only do negative work, which makes for a fun joke. Okay, so we have a few more minutes before we actually have to start the lab. Work leads us to energy, okay? Here we go.
That's a terrible joke.
Thank you. So remember, we have types of energy, all right? In this class, we're primarily going to talk about mechanical energy, okay? But there's other types of energy. And remember, energy isn't created or destroyed. You can just move it from one form to another. And side note, mass is also energy. We'll get there. That's the whole E equals mc squared thing. But thermal, we have mechanical energy, right? We have thermal energy. We have electromagnetic energy. We have chemical energy and nuclear energy. Okay, and pretty much anything can be categorized as one of these types of energy, depending on your perspective. Now, we're primarily going to be talking about mechanical energy. In terms of mechanical energy, we have two types, and there's only one we're really going to care about today, but the second one's there by periphery. Gravitational potential energy, which comes from work, and we'll do this derivation later. Gravitational potential energy is represented by a letter U. In this case, it's going to be mgy. Okay? So, in a closed system, energy is always conserved. Okay? Now you can lose energy out of your system in various ways, either with work that goes outside the system, or with heat, or sound, or anything like that. But in general, energy can be conserved for things that are not running into other stuff. Okay? So if energy is conserved, and by that we mean mechanical energy, we have two types of energy. We have kinetic energy, and that's represented by K, and it's 1/2 mv squared. Okay, where this is velocity, this is mass, this is your kinetic energy. All right, we'll go into how we actually get this next time. Okay, it comes from work. There's a lot of other things we need to go over. But there's two types of kinetic energies. This is linear. There's also a rotational one. We're not going to get that until we have to define things like center of mass and moment of inertia to understand that. So let's start with just the idea that this is kinetic energy. And this equation is really important, and you'll have to remember it for the rest of forever. Okay. And then we have potential energy. Now there are lots of different types of potential energy. But in physics, when we're talking about mechanical potential energy, we primarily talk about two, and then we add a couple when we get into electromagnetism. But in physics, we have gravitational potential energy, which is mgy,
Where y is height.
where y is the height. Because remember, we can do work against gravity, and you'll notice this looks a lot like work. Force times displacement. Okay? So you do work, you get gravitational potential energy. So if you do work against gravity, you store gravitational potential energy. You can also have spring potential energy, which isn't going to be as important in the lab, although it is there is a spring involved in the lab, but you don't need to know what it's doing. But it equals 1/2 kx squared. You don't need to know this for the lab, but it might help you understand sort of the concepts. Okay? So if you have something that doesn't collide with anything, or basically no collisions, no friction, if you start with this much potential energy, this is how much kinetic energy you'll get out. Okay? So this plus this at any point always equals this plus this at a later point. Okay? So if for instance, you have this thing, and let's say we hold it a meter off the ground, we know mgy, let's say it equals 2 joules. Okay? Right before it hits the ground, because what happens when it hits the ground? That's a collision. So energy is no longer conserved if there's a collision or friction. So friction, okay? Right before it hits the ground, whatever you got for mgy should be equal to 1/2 mv squared right there. In between, right, as y gets smaller, you get mgy plus 1/2, whatever the speed is, mv squared. Okay? So you're changing from potential to kinetic energy. Here, it's right before it hits the ground, it's going to be all kinetic, right? So as you drop it, it goes faster and faster and faster. The kinetic energy gets bigger. Because it's going down, the potential energy is getting smaller. So as the height gets lower, changes more of the stuff from potential into kinetic. Okay? So, just as a sort of, there's a little graphic here. Here's sort of what we're talking about, right? As you go up and down, you're converting back and forth between potential and kinetic energy. Okay? When you're higher up, you have more potential energy. As you fall farther down, you have more kinetic energy because you're going faster. Okay? All right. Here's another visual. Okay? So right now, kinetic energy. Convert that to elastic and gravitational potential energy, then it goes back to kinetic energy. Okay? So just a general idea. What happens when you have a collision? Then you have to be concerned about something else. So we know energy is not generally conserved in a collision, but there is some. We have this scalar product of two vectors. So we talked about work. What are the two important physics variables involved with work? Force and displacement, right? So if you're lifting something heavy but not lifting it very far, that could be the same as taking something light a long distance, all right? So in order to do that, it turns out the other thing that matters is angle. And we'll talk about that in a minute, but let's talk about the scalar product, or the dot product, okay? So the dot product of two vectors looks like this, where when you have these two things, and you have an angle, let's call it phi in between them, it's A dot B is AB cosine phi. Now, what does the dot product really measure?
It's a scalar quantity.
Well, no, but like in terms of like the physical things we're dealing with, why do we usually need a dot product?
You usually look for orthogonality or
Close, right? You want to see how parallel two vectors are, because it turns out for work, right, you want the force and the displacement to be parallel. Now we've talked about situations where they're parallel or anti-parallel. Remember, we have that guy pushing the rock up the hill. If he's pushing the rock up the hill and the displacement is also up the hill, that's positive work. If he's pushing this way and the rock's going this way, that's negative work. And if he's pushing and it's not moving, that's zero. But what if he were pushing a rock up and it moves to the side? Okay? So there's other displacements that aren't necessarily parallel to the force, and we have to figure out what to do with those too. So it turns out a dot product, from a mathematical perspective, basically you're taking the component of B along A and multiplying the component of B along A and A, or you're taking the component of A along B and multiplying that together with B. But you're making the two vectors parallel, and you'll notice when you take a component of B along A, is it going to be all of B? No, it's just part of it, right? So you have B cosine phi, and that would be parallel to A, and then you can multiply them together because they're parallel, okay? So you're looking for a dot product. It measures the parallelness of two vectors, all right? That's the sort of physics-y definition of it. So for instance, if we have this situation that we've talked about over and over, we have a force going this way and a force going that way. That gives us a net force, okay? And let's say the displacement's this way. Here's our force from this is, if this force is going this way, here's an angle between those two vectors, okay? You need the component of this force that points along this vector. That would be F cosine theta, all right? If you look at the work done by this person, then that's going to be F cosine theta delta R, okay? It's not their total force, it's just the force that's parallel to the displacement. All right, so we're now looking at it. Work is not just force times displacement. Work is force as a dot product of displacement. Okay, so it's F displacement cosine 30. And it actually gets a little bit more complicated because what are we assuming about the force here? That it's constant, right? So if it's not constant, what else do we have to add? Integral. Okay, then we have to integrate the force over the displacement. But for now, let's just talk about the dot product part. All right. So if we have force and displacement, this is what we've been already talking about, okay? If these two things are parallel, then work is positive. You have F dot R. What's the angle between these two things? 0, okay? So in the case where you have parallel vectors already, then cosine 0 gives you 1. We go back to it just being force times distance, okay? If you're anti-parallel, what's the angle? 180. What's cosine of 180? Negative 1, and that's how we get this negative work. All right. What about here?
90, 0.
Yeah, this is 90 degrees between these two vectors, which means our dot product gives us 0. Okay. So here's another riddle. Why are centripetal forces so lazy?
They're perpendicular to the force.
Because they never do any work. Because if you have a centripetal force, which way does it point? Towards the center of the circle. Which way is the displacement? Tangent to the circle. Okay, so your force is in the radial direction, your displacement is in the tangential direction, and they're always at an angle of 90 degrees, which means centripetal forces can't do work. Okay, what did friction do?
Negative work.
Negative work. Okay, so friction always opposes motion, which means it's always in the opposite direction of displacement, so it does negative work. Centripetal forces are always perpendicular to your displacement, which means they don't do work. Okay? All right. So yeah, this is just sort of a picture of that. If your velocity is this way, that means your displacement is this way. If this is your force, the angle between these is 90 degrees. Okay? All right. Now that we've gotten all the jokes out of the way. That was a quick question. Much better. Okay, so what's the work done by this force? 0. Okay. What's the work done by this force?
4 newtons.
4 delta R, right? So this is 0 delta R. This is 4 delta R. What about this one?
6
delta R. So this one's the biggest. Okay. This one's the next biggest. This one's 0. So the largest one is the 6 Newton force. Everybody remember cosine 60 is 1/2. Okay. And if you don't know that, I'm sure your calculator or phone does. Okay. So now we're going to add one more thing into the math. All right. A variable force is a force that changes over displacement, for instance. Okay. So the most formal definition of work looks like this. Okay. So all we've done is we've changed, force is still there, but we've changed delta R to dr. Okay, what does this look like? Well, if we want to see the work done from here to here, what do? Area under the curve, right? So if this is your initial position and this is your final position, you just figure out this area. Okay? So the work in this case is represented as an area under the curve. Now, what is this a graph of?
It looks like a graph of an upside down. Or
No, not like what do you see in the clouds when you look up. Like what are we talking about when we graph force? Okay? So what axis is this? Force. Why is there a subscript x?
In that
In the x
direction.
direction.
Yeah, it's the force in the x direction. Okay? This is the x direction. So as you move in the x direction, the force gets bigger and then it gets a little smaller again. Okay, so that is a variable force, which means, let's say this is 2 newtons, right? You start out with a force of 2 newtons. As you move along, as you're pushing, and you end up with something like 4, and then you go down to like 3.5. Okay, so we're changing the force over distance, not time, distance. Okay, so the work in this case is going to be variable. All right, so your total work, you get that by varying the force over your displacement. Now, what is an example of a force that changes over distance?
Magnetic field.
Magnetic
Like,
fields change, yeah. Electromagnetism, that works pretty well. Here's a real basic one. Springs, okay? When a spring's not stretched, when it's just hanging out, when you haven't stretched or compressed it, how much force does it have?
0.
0. What if you stretch it?
It has.
Like a
More
negative.
force, right? So for instance, if I get a rubber band and I aim it at you, would you like it to be shot at you when it's stretched a little bit or a lot?
A lot.
Okay, assuming you're not like a weird masochist, all right? Assuming you don't want to get hurt. You don't want the rubber band stretched as much. Why? That's less force, okay? So as you displace the rubber band, right, as you're stretching the rubber band, what are you doing? Storing energy, all right? You're storing spring potential energy. So you're doing work on the rubber band as you stretch it, okay? The more you stretch it, the harder it gets to stretch. So it's applying more force back on you as you stretch it further. So this is an example of a force that varies over distance, okay? A small displacement of the rubber band means a small force. A large displacement means a large force. So if we have springs, right, the spring exerts a restoring force whenever it's stretched or compressed. So if you stretch it this way, it tries to go back this way. If you compress it this way, it tries to go out the other way. That's what this negative sign means, okay? So when we talk about the spring force, as you stretch a spring that way, the force goes back this way. But this is a displacement. And why is this written as a displacement? It's because it's the displacement from the equilibrium length. And what is an equilibrium length for a spring or a rubber band? Yes?
When it's at rest, like when you just let go and it stops moving.
Yeah, but it's just like hanging out, okay? So if you have a spring that's just sitting there, that's its equilibrium length, okay? So what we're talking about, when we talk about K delta S, it's not the total length of the spring, it's the displacement from the equilibrium. So if you take something and you stretch it a little bit, it's the distance from here to here, not this whole distance, okay? So a spring exerts a restoring force whenever it's stretched or compressed. Here's our force. That means if the displacement goes this way, which way is the force? The opposite way, okay? What's this?
Spring constant.
Something called the spring constant, okay? What is the spring constant?
It's the springiness of a spring.
It is. That is actually a good explanation. It is the springiness of a spring or the stiffness of a spring, okay? So a large spring constant, you would assume that's pretty stiff, okay? If it's a really like bendy string, like a slinky, then it would have a small spring constant, all right? So this tells you the stiffness of the spring, this tells you the displacement from equilibrium, and this tells you whichever direction you stretch or compress the spring, the force goes the other way, okay? Yes?
Is K a variable?
K is not a variable. K depends on the spring. So as long as you have the same spring, you have the same K. Okay, the only time that we get out of this realm of where K is constant for our spring is if have you ever stretched a spring or a rubber band so far that it doesn't quite go back to where it came from? Yeah, so that's called going into the plastic range, where you actually change the material that you're using by damaging it, by putting too much force on it. Yeah, you deform it. So we're not talking about that. We're talking about all reversible processes, okay? So K just depends on the spring. All right? So if we want to look at this, here we have 3 springs. They're all the same spring. They're all unstretched. So this would be the equilibrium length, okay? Here's unstretched. Then if we stretch the spring, what's the displacement? So which way does it point? This way, okay? So that means we have a displacement from here to here, all right? Our displacement points that way. Which way is the force point?
Left.
Back the other way, okay? We can also compress our spring, right? And then we have a displacement this way, and then the force goes that way, all right? So hopefully that's a reasonable if we wanted to plot this, okay? Because before we had a plot of force versus displacement. So as we increase the force, what happens to, or as we increase the displacement, what happens to the force? Increases, okay? So if you wanted to plot that, it looks something like this, okay? Now why is the slope negative?
Because it's a negative coefficient.
Because as we increase the force in this direction, as we increase the displacement in this direction, the force is in the negative direction. So the force goes down, okay? So this is a plot of position versus force. So if we wanted to figure out the work from here to here, what do we do? Yeah, so the amount of work it takes to compress the spring like this, we would integrate under this curve, okay? And then we would be, once we found the area of that triangle, that's the work. All right, so that would be K times X, let's say X max, where this is the maximum compression, okay? So if you wanted to figure out what that is, it would be, so here's your force, Kx max. Here's your displacement, X max. What's the total area here?
You multiply them and divide by 2.
Yeah, it's the area of a triangle. So 1/2 base times height. So 1/2 K X squared. Okay? So when we think about the energy of the spring, if we do work on a spring, you get potential energy. When you do work on a spring, if you integrate under this curve, you're always going to get 1/2 kx squared. All right? So 1/2 kx squared is the potential energy of a spring, and that's just from the area under the curve. Because remember, we do work in order to store potential energy.
A 1.5 kilogram model rocket is launched straight up from rest. The thrust from the rocket is 40 newtons. What is the speed of the rocket when it is 50 meters above the ground? Well, first let's draw a free body diagram for this situation. So we have here, here's our free body diagram. So we have the thrust upwards. And we are also going to have gravity downwards, which we'll represent as mg. Right? We're assuming the thrust is stronger than gravity, and we'll call it F thrust. And so what are our knowns at this point? Well, our knowns are that the force of the thrust is 40 newtons, that the mass is 1.5 kilograms, and that delta y is 50 meters. So that's what we know so far. What equations do we need? Well, we want to calculate, we're going to use basically the relationship between the work, right? Work net is equal to the change in kinetic energy. We're going to use that to find the final speed of the rocket, assuming, it starts from rest, so we can find K final. And we need to remember that the kinetic energy is 1/2 mv squared, and that the work done by a force over a distance, this might come in handy, maybe or maybe not, is force times the distance traveled. So these are the equations that we're going to need. So let's calculate our solution then. So our solution is, let's start by first calculating the net force. The net force is going to be the sum of the two forces on it, right? So we're going to have the force of the thrust upwards minus the force of gravity downwards. And so the force upwards we saw is 40 newtons, and the force downwards due to gravity is 1.5 kilograms times good old 9.8 meters per second squared. And when I work all that out, I get about 25.3 newtons. We're also going to need the net work, right? So work net is going to be equal to F net times delta y. And so that is, we have our two values, right? Our F net is 25.3 newtons, and our distance that is traveled is 50 meters. It goes up 50 meters. And so using that, we can calculate that the work done is 1265 joules. So now we know the work done, and we can use all this to calculate the final speed. So let's use our work kinetic energy theorem, and that is that work net here, let me write over a little bit here. Work net is equal to the change in kinetic energy, or work net is equal to K final minus K initial. Now, since it starts from rest, we can say that K initial is 0. So let's plug in for our kinetic energy. So work net is going to be equal to 1/2 m v final squared, and that's what we're trying to find, is v final. So let's solve for v final, right? Solve for v final, and if you invert that equation, you get that v final is equal to the square root of 2 times the net work divided by m. I'm going to plug in all, so now we're going to plug in our values into here. So if I plug in my values, I get 41.1 meters per second. So that's how fast it is going at the end. And that is our solution to this problem.
Perspective it is whether it's positive or negative. Okay? All right. You guys want to try a work problem?
Sure.
So exciting. All right. Here's the problem. It's always good when you use graph paper and then the graph doesn't match the graph paper.
The graph shows the force exerted by a spring on a mass as a function of distance that the spring is compressed or stretched. How much work did the spring do in bringing the mass from x equals 4 to x equals 2 meters? So to go from x equals 4 to x equals 2 meters, so it starts here and it goes to here, right? And we're going to calculate the work using that work is equal to the integral of the force dx from x initial to x final. So we're plotting force versus x, and we want the integral of force over x. So the area we're going to need is related to this area here, right? The area between the graph and the x-axis. Now, because we're integrating right to left, the work required is going to be the negative of this area. And since this area is already negative, that means it's going to be a positive value, right? So we need this area. So let's look first at this part here. This part here is easy. That area here, well, we'll call it area 1, is just 2 times 2, right? So it's 2, the change in F is 2 meters times, it goes down 2, so 2 newtons, so it ends up being 4 joules. And then if we look next at this second part here, right, that area there is going to be equal to, it's the area of a triangle, right? So it's going to be, this area here is going to be 1/2 the base, which is 2 meters, times the height, which is 2 meters, and that gives us 2 joules. So we have up here, if I had drawn it correctly, we would have 4 joules and 2 joules. So our work then, based on this equation here, will just be the area underneath that graph, so it'll be A1 plus A2. So the total work will be 6 joules.
Positive. Okay. All right.